Very good morning, students. So this is the new video of the chapter electric potential and capacitance. Here in this video we are going to see what can be the energy stored in a capacitor. If a capacitor is being charged with the help of some potential source, here you can see potential source is a cell. So if this cell is charging the capacitor, then what is going to be the potential energy of the capacitor after charging? So energy stored in the capacitor is on account of the work done by the charging potential or potential source to transfer certain amount of charge on the plates of the capacitor. It means we are going to calculate what is going to be the amount of work done by the potential source to charge the capacitor. So initially, suppose there is charge Q dash on the plate of the capacitor is existing before charging starts. So potential difference between the plates of the capacitor is V dash, and that can be given V dash is equal to Q dash, that is amount of charge on the capacitor initially divided by capacitance. Now if a small amount of additional charge dq is to be transferred on the plate of capacitor further by the cell or the potential source, then what is going to be the amount of work done? See, work done to transfer unit charge on the plate of the capacitor is potential difference between the plates. If dq charge is to be supplied further, the amount of work done is going to be work done for unit charge multiplied by amount of charge to be transferred. So work done to transfer dq dash charge on the plate of the capacitor, dw can be written V dash multiplied by dq dash, or V dash is replaced by q dash divided by c. So work done to transfer dq dash charge on the plate of the capacitor, dw is equal to q dash divided by c into dq dash. Suppose this is equation number 1. Now to generalize this condition, suppose initially there is no charge on the plate of the capacitor, means value of charge q equals 0, and when this capacitor is charged fully, the amount of charge becomes q. So if we integrate equation number 1, you can see at the right hand side of the equation variable is charge q. Capacitance of the capacitor is to be treated as a constant. So if we integrate equation number 1 with limit 0 to w dw equals limit 0 to q dash divided by c into dq dash. So after integration of dw is w, 1 by c, it's a constant. Integration of q dash dq dash by formula integral x dx, the integration is going to be q dash square divided by 2 with limit 0 to q. So what is the work done to transfer charge q on the plate of the capacitor? That is going to be w equals 1 by c into q square divided by 2. And this amount of work done by the charging potential source is defined as the electrical potential energy of the capacitor. What is the definition of the electrical potential energy? Work done in charging a capacitor is stored in it as electrical potential energy. So work done to charge the capacitor, this is going to be potential energy of the capacitor after the charging completes. So what is the formula for the potential energy stored in a capacitor after charging? That can be written U is equal to Q square by 2 into C. This is first formula. But as we know, relation between charge, capacitance and potential, Q is equal to C into V. So if we replace value of Q as C into V, the energy stored in the capacitor U is equal to 1 by 2 C into V square. This is second formula to calculate the same quantity, that is energy stored in the capacitor. If we can write Q is equal to CV in this equation, the formula becomes U is equal to half Q into V. This is third formula. So to calculate the energy stored in a capacitor, all the three formula can be used. If charge is stored on the capacitor and capacitance is known, this is formula 1. If capacitance and charging potential of the capacitor is known, then we can use second formula. If charge is stored on the capacitor and charging potential is known, we can use third formula. So using any of the three formula, we can calculate the energy stored in a charged capacitor. Students, see, there is another quantity related to a charged capacitor. What is energy density of an electric field between the plates of the capacitor, or you can say what is the energy density of a charged capacitor. So energy stored per unit volume of an electric field is energy density. Suppose this is a parallel plate capacitor. Separation between the plates of the capacitor is D. Area of the plate of the capacitor is E. What can be the value of electric field at any point in between the plates of the capacitor? That is given as E equals sigma divided by epsilon naught, where sigma is charge density. If positive charges are spread uniformly over this plate of the capacitor, same amount of negative charges are there. So what can be the value of charge density? Sigma. Sigma equals electric field multiplied by the epsilon naught. Charge on the either plate of the capacitor, by the equation sigma equals charge by area of the plate, we can get Q is equal to sigma multiplied by A. So charge on the either plate of the capacitor is Q equals sigma into A. If we replace value of sigma as E into epsilon naught, then charge on the plate of the capacitor is Q equals E into epsilon naught multiplied by A. Energy stored in the capacitor, when this capacitor is fully charged, storing charge Q, then energy stored in the capacitor by the first equation, U equals Q square by 2C. Then value of Q here, if we put this value of Q, so value of Q square is epsilon naught square E square A square divided by capacitance twice the capacitance of the capacitor, epsilon naught A by D. Epsilon cancels, A cancels, D multiplied here. The energy stored in the capacitor can be written as half epsilon naught E square, where E is electric field, A into D. So let's see, A into D. What is A into D? A into D is volume of the region between the plates of the capacitor, this volume. So energy stored in the capacitor is this, and volume of the capacitor is A into D. So that what is the energy stored per unit volume of the capacitor? U dash equals energy stored divided by volume. Volume cancels, half epsilon naught into E square. So this would be the value of energy density of the capacitor, or energy density of the electric field between the plates of the capacitor. Students, see in this part of the video, what is combination of capacitors or grouping of capacitors in series and parallel. What is the necessity to group the capacitors or to combine the capacitors? Students, as you know, the capacitor has a fixed value of capacitance. Many times if we are having capacitors of same value, but need to apply the capacitance of the different value in a circuit, in that condition we can group the capacitor either in series combination or in parallel combination. First of all, see what is series combination of capacitors. In series combination of capacitors, suppose capacitors of capacitance C1, C2 and C3, three capacitors are there. First plate of the first capacitor is connected to positive terminal of the cell or battery, which is going to supply the electrical energy to this combination. The second plate of the first capacitor is connected to first plate of the second capacitor. Second plate of second capacitor is connected to first plate of third capacitor, and so on. And second plate of the last capacitor is connected to negative terminal of the battery or the cell. Then this type of combination is called series combination. See what happens in the series combination of capacitors. Whatever amount of charge is stored by the first capacitor, all the capacitors in that series going to store same amount of charge. Means in this combination, charge stored by the capacitor Q remains same for all capacitors. This is the condition necessary for the capacitors to be in series combination. See why this happens. Suppose the first plate of the capacitor C1 is stored positive Q charge. Here, there is going to be induction of the same negative charge on the second plate of the capacitor, and induction of same amount of positive charge on the second face of the second plate of capacitor C1. That positive charge is supplied to first plate of second. Then this process continues. So whatever amount of charge is stored by the first capacitor, that going to remain same for all the capacitors, whatever is the capacitance of capacitors may be in series combination. But as their capacities are different, C1, C2, C3, they are not equal. In that condition, potential difference across the capacitors going to be different. Potential difference across first capacitor V1, across second capacitor V2, across third capacitor P3. So if we calculate value of the potential difference across individual capacitors, we can write V1 equals Q divided by C1. Potential difference across second capacitor V2 equals Q divided by C2. Across third capacitor V3 equals Q divided by C3. As Q is remaining same. So what is the total potential difference? V, that can be written V is equal to V1 plus V2 plus V3. Now suppose the equivalent capacitance of this series combination is CS. Then what can be the value of V? Q divided by CS is equal to Q by C1 plus Q by C2 plus Q by C3. Q as being common, charge cancels out, and formula for the equivalent capacitance CS, reciprocal of that, 1 by CS equals 1 by C1 plus 1 by C2 plus 1 by C3. So using this formula we can calculate equivalent capacitance in series combination of the capacitors. So students, remember, in series combination of resistors, the formula is written as RS equals R1 plus R2 plus R3. And for series combination of capacitors, formula is entirely different. So remember this difference of combination of resistors and combination of capacitors. Students, see, this is parallel combination of capacitors. In parallel combination of capacitors, first plate of all the capacitors are connected to a common point, and that point is connected to positive terminal of the cell or battery. The second plate of all the capacitors connected to negative terminal of the cell or battery. Students, in this combination of the capacitors, the potential difference across capacitors remains same, as all the capacitors are connected between negative and positive terminal of the same battery or the cell. But As the capacity of the capacitors is different, they can store different amount of charges. So in this combination or grouping of capacitors, potential difference remains same, but charge stored by the capacitor is different. So what can be the value of charge stored by the first capacitor? Charge stored by the first capacitor Q1 is equal to C1 into V. Charge stored by the second capacitor Q2 equals C2 into V. And charge stored by the third capacitor Q3 is equal to C3 into V. So what can be the total amount of charge stored by this combination? Charge stored by the combination Q is equal to Q1 plus Q2 plus Q3. If capacitance of the combination or equivalent capacitance of the combination is written as Cp, then we can write Cp into V is equal to Q1 plus Q2 plus Q3. So C1V plus C2V plus C3V, as V is common, cancels out, and capacitance of this parallel combination, equivalent capacitance, can be written Cp equals C1 plus C2 plus C3. This is going to be the formula for equivalent capacitance of parallel combination of capacitors. C1 plus C2 plus C3. And similar formula is used in the case of resistors in series combination. So this is different between capacitor and the resistor combination. Students, let us see some numericals to find equivalent capacitance of a network of capacitors. Here you see this is a question. To find equivalent capacitance of this network of capacitors between point A and B. The question is find the equivalent capacitance between point A and B as shown in the figure. Network is given in the figure. Also calculate the total charge that flows in the circuit when a 100-volt battery is connected between points A and B. So first of all, we have to find what can be the equivalent capacitance of this combination. Students, in this figure you can see these three capacitors are connected in series. Whatever can be the shape of that connection, but if the capacitors are connected end to end, they are to be considered in series combination. These three capacitors are connected in series and these two capacitors are in parallel. If you solve this series combination, what can be the capacitance of this part? By the formula 1 by Cs equals 1 by 60 plus 1 by 60 plus 1 by 60. So 1 by Cs is equal to 3 by 60, 1 by 20, and Cs is going to be 20 microfarad. So this total capacitance of this series combination is 20 microfarad. Now this part, these two capacitors are in parallel. If you solve this, the capacitance is going to be Cp equals 10 plus 10, again 20 microfarad. So student, when you initially start solving this network of the capacitors, it is a good practice if you redraw the network after each solution. Afterwards, when the practice is perfect, then you can solve the network without any redrawing. Now if you redraw this, you can get A, point A is here, 40 microfarad capacitor. This 40 microfarad capacitor is in series with these two capacitors. Now the circuit looks like two capacitors of 20 microfarad in parallel. This is 20 microfarad, this is 20 microfarad, and this is point B. Now, before we proceed, we have to solve this parallel combination of these two capacitors. So what is their value? You can write Cp dash is equal to 20 plus 20, that is 40 microfarad. Means this capacitance is 40 microfarad. Now if you again redraw this circuit, there are going to be two capacitors of 40 microfarad each in series combination, 40 microfarad and 40 microfarad. Now series combination of 40 microfarad capacitors, what going to be the value? If you again use formula for the series combination of this, you can write 1 by Cs dash is equal to 1 by 40 plus 1 by 40, or 1 by Cs dash is equal to 2 by 40, and value of Cs dash is going to be 20 microfarad. This would be the equivalent capacitance between point A and B for this network of capacitors. Now the equivalent capacitance of this network is 20 microfarad. The second part of the question: if a battery of 100 volt is connected between point A and B, what going to be the amount of charge stored in the combination, or you can say what going to be the amount of charge that flow through this network? So to calculate amount of charge, by formula Q equals C into V. So equivalent capacitance of the circuit, amount of charge Q is going to be 20 microfarad, that is 10 to power minus 6, multiplied by applied potential, that is 100 volt. It's going to be 20 into 10 to power minus 4 coulomb. This would be the second answer. 20 into 10 to power minus 4 coulomb.